Next, we're going to talk about exponents, which we're going to be using a lot in this course. So let's say that we have a and b, and they are positive, and x and y are real numbers. So x and y are part of the real number set. The first rule that we have is going to be that if we have b to the x times b to the y, this is going to be equal to b to the x plus y. Our second rule that we're going to need to know is that if we have some constant a times some constant b, and this is to the x power, this is going to be the same thing as a to the x times b to the x. Our third rule is going to be that if we have b to the x over b to the y, this is going to be equal to b to the x minus y. Our fourth rule is going to be that if we have some constant a divided by some constant b, and this is taken to the x power, this is the same thing as saying a to the x over b to the x. Our fifth rule is that if we have b to the x power taken to the y power, this is equal to b to the x times y power. Our sixth rule is going to be that if we have any constant to the 0 power other than 0, this is going to be equal to 1. Our seventh rule is going to be that if we have a to the minus x, this is going to be the same thing as 1 over a to the x. So a negative power will make it 1 over the constant to that power. And our eighth rule is going to be that if we have a to the x over y, this is going to be the same thing as taking a to the x power and taking the yth root of that a to the x power. These are all really important rules that we're going to be using a lot, because a lot of times when you're doing calculus, the part students struggle with most is the algebra. It's you get it into some form, but then what can I do with it in order to cancel things out, simplify, things like that. While talking about exponents, I also wanted to bring up Euler's number, which is represented by e. And this is a number that is roughly equivalent to 2.71828, so on and so forth. It's an irrational number that goes on changing forever. The function f of x equals e to the x is a natural exponent. And the nice thing about this is it actually has some really nice properties when we're doing derivatives. Another thing is that Euler's number e is special because the slope of the tangent line at f of x equals e to the x at 0, 1, it has a slope of 1. Next, what I want to do is I want to cover some definitions that we're going to be using and are often going to come up in a lot of math classes, but particularly in calculus. And the first is a one-to-one function. So a one-to-one function, which you may also see it as 1-1. And what a one-to-one function is it's a function that can never take the same value twice. That is to say that if I have some function and I have the value x1, it will never be the function at x2 where x1 does not equal to x2. So what this means that if I plug in some number into my function and I plug a different number in, meaning that they're not equal to each other, it will always be a different number. So an example of this might be something like if we were looking at a natural log or something like this, where it'll never be the same number twice. No matter what x value I plug in, I will always get a different outcome from my function. One of the nice properties of a one-to-one function is that it passes both the horizontal and the vertical line test. So some of you all may have seen the vertical line test to test whether something is a function, where if you were to cut it in any place with a vertical line, it doesn't cross through the function more than once. But also, if it's one-to-one, it also will pass the horizontal line test, meaning that if I were to cut this with horizontal lines, it would not pass through the function more than once. This can be especially useful when we're looking at our next thing, which is inverse functions. So an inverse function is that when you have your domain of a function, x, and your range of that function, y, the inverse of it will have a domain of y and a range of x. So what this means is that the way we write an inverse function would be f of minus 1 x. And this is basically just telling me that this is the inverse of my function f of x. And then if I were to take the function of the inverse, that is to say, if I were to say f of negative 1 of x, what this is going to give me is this is going to be equal to whatever was within the function, because the inverse function undoes it. So if I plugged x into the inverse function and then I took the function of it, it would undo that inverse function. I would just be left with x. Similarly, if I have f of x and I take the inverse function of f of x, this also will undo the function. So whatever x you plug in, the function will transform it into whatever outcome you get. The inverse function will undo that and take you back to x. The graph of an inverse function will reflect this function over the y equals x line. So when y equals x, that is to say this line here. So if I have some function that looks like this, what it's going to do is it's going to take this and reflect it across the y equals x axis, and it will be something like this. So all it will do is it will reflect across the y equals x axis. And then of course, one last thing, because of this property where basically everything is inverted, if I have on my f of x some point a, b, then this means that the inverse function will have some point b, a. Next, I want to talk about logarithmic functions. Now, I know most students hate these, but they are actually tremendously useful in mathematics. They're really good to act as a scaling factor, and if you have some, functions that grow very quickly, they can actually help bring it down into a scale that's very useful for us to analyze. So if b is greater than 0 and not equal to 1, then the exponential f of x equals b to the x is 1 to 1, and the inverse is the logarithmic function. That is, f of x equals log base b x. So what this means is that if we have b to the y, this will equal to x, and that means that if we solve for y, we have y is equal to the log base b of x. And this is kind of how we do this whenever you first learn logarithms. You learn about the logarithm function, and then you learn about the inverse function to figure out what your x would be and things like that. Now, this isn't really what we're going to be focusing on in this course. What I really want to be focusing on are the laws of logarithms. So just like before when we were doing exponents, we have a bunch of rules that really help us with our calculations. So the first is that if I have log base b to the x, this is going to just be equal to x. So pretty much the way it works is that I can pull this power out and it will just become x times log b to the b, log b of b, and then it'll just be x. The second law is that if I have b to the log base b of x, this is going to be equal to x. This is actually using these rules here. So if I have that y is equal to log base b x, this is the same thing as saying b to the y, which looking at this, we have that b to the y is equal to x. So it's actually just from our definitions of the function for the logarithm and the inverse. The third law is going to be that if we have log base b of 1, this is going to be equal to 0. The fourth law is going to be that if we have log base b of x times y, this is the same thing as taking the log of x plus the log of y. And this is actually one that we're going to use quite a bit in this course. Similarly, if I have log base b of x over y, this would be equal to the log base b of x minus the log base b of y. And then our last rule is going to be that if we have log base b of x to the r, this is going to be equal to r log base b of x. And this is kind of similar to what we were talking about up here of pulling the powers out, is that basically what this means is that I can pull powers out. So this is also one that we will use quite a bit in this course. Now, generally, we're not going to be using logs in terms of base b. We're actually going to be using what's called the natural log. So the natural log is just going to be the log with base e of x. And you'll actually find this, for example, if you look at your calculator, you'll see that you usually have a special button just for this. And then these are the natural logs. So whenever you see natural log of something, this is what we're doing. We're taking a log with base e, and this we're actually going to be using quite a bit. But let's say that you actually had some logs and you wanted to change the base from one log to another. So if we had log base b for some value a, then what we could do is we could take the natural log of a over the natural log of the base that we had for this logarithm, which would just be equal to log of a over log of b, which then is going to be equal to log of x a over log of x on b. So again, we're not going to use this a ton, but it is useful to know this just in case you ever do need to change the base of your logarithm. Now we're going to talk about sequences. So a sequence is just an ordered list of numbers, a1, a2, ... through an, and then it continues on. And sequences can be defined either explicitly with a formula or recursively. So for example, let's say that we have an equals 2n minus 3. If we were to start plugging in numbers into this, what would we get? So if we plugged 1 in for n, so a1, we would get 2 times 1, which is 2, minus 3 gives us negative 1. If we were to plug in 2, we would get 2 times 2 is 4, minus 3 is 1. If we were to plug in 3, we would get 3 times 2 is 6, minus 3 is 3. If we were to plug in 4, this would be 4 times 2 is 8, minus 3 gives us 5. And then, of course, this could go on and on. So you can see that what's happening with this sequence is that it's taking your input number and it is increasing it by 2 every time that you go up by a number, starting at negative 1. So negative 1 to 2, negative 1 to 1, 1 to 3, 3 to 5, 5 to 7, 7 to 9. And then this sequence would go on forever. So this explicitly defines what the sequence is. Let's say, for example, then that we have the sequence bn, and this is equal to negative 1 to the nth power divided by n plus 1. So what's going to happen when we start plugging numbers into this? Well, if we plug in b1, we're going to plug in 1 for the 1 power. So negative 1 to the 1 power is negative 1. And then 1 plus 1 is 2. So we get negative 1/2. If we plug in b2, when we plug 2 in, this becomes negative 1 squared. Negative squared gives us a positive. So this will be positive 1 over 2 plus 1 is 3. If we plug in b3, what we get is negative 1 cubed, which again will be negative 1. And then 3 plus 1 is 4. b4 is going to be 1 over 5. So looking at this sequence, what's happening is that it's actually alternating. So it's going from a negative value to a positive value, negative value to positive value. But each time it does, the denominator is going up by 1, meaning it's actually getting closer and closer and closer to the origin. It's bouncing back and forth from negative to positive, but each time it's getting a little bit closer, and it's approaching with every single number. Now, what if you actually have the sequence and you wanted to try to figure out what the explicit definition of that sequence is? So let's say, for example, you have 7, 11, 15, 19, and so on and so forth. And we want to figure out what is the sequence that describes this. So usually what I would do is I would consider what times some value n, or to some power, and then added something would cause the sequence to occur. So what's happening here is we're going from 7, and we're increasing by how much? 7 to 11 increased by 4. 11 to 15 increased by 4. 15 to 19 increased by 4. So this means that I know that every step of the way, I should be going up by a factor of 4. And then I need to figure out, well, what would cause me to start at 7? So if I plug in 1 here, 1 times 4 is going to give me 4, plus what makes this 7? So this would be 4n plus 3. And then if we just check our numbers, 1 times 4 is 4, 5, 6, 7. 2 times 4 is 8, 9, 10, 11. 3 times 4 is 12, 13, 14, 15. 4 times 4 is 16, 17, 18, 19. And this seems to fit the sequence for the numbers that we have. Or let's say that we have 2 over 3, negative 4 over 9, 6 over 27, negative 8 over 81, so on and so forth. Now for this one, because it's going from positive to negative, generally this means that we're going to have some value to a power, which will basically go from an odd power, which would usually either make it negative or positive, and then you're going to flip it based on whether it's something like negative 1 to the n plus 1 power or negative 1 to the nth power. So the fact that our first term is going to be positive, this means that likely it's going to be to the n plus 1 power. So I'm going to start with this. So minus 1 to the n plus 1 power. So basically what's going to happen then is if I plug in 1, I get negative 1 to the second power, which means that this will be positive 1. If I plug in 2, this is going to give me negative 1 to the third power, which means it would be a negative 1. So okay, so that part looks pretty good. Now, just like before, I'm going to look at my numerator and see what would cause these numbers to occur. So basically what's happening is that it's increasing by 2 each time. So if I were to plug in 1 times what gives me 2? 2 times what gives me 4? 3 times what gives me 6? So this means that it's probably going to be 2n. And now we want to focus on the denominator. We have 3, 9, 27, 81. Now I can see from this sequence that this is going to be powers of 3. 3 to the first power is 3. 3 squared is 9. 3 to the third power, or cubed, is 27. 3 to the fourth power is 81. So I would say that this is going to be over 3 to the n. And now we have the function that describes this sequence. The last thing I want to talk about are recursive sequences. So recursive sequences are where you take the output from one step and put it into the next step. So it basically will change recursively from each step and what came before. So let's say, for example, that we have a1 is equal to 4 and an is equal to 2 an minus 1, which means the prior a that you had, so before this step, plus 5. So to begin our sequence, we have that a1 is equal to 4. So we're already given the first step. Now what I'm going to do is I'm going to take that 4 and I'm going to plug it into here. So I'm going to get 4 times 2 is 8, plus 5 is going to give me 13. And now what I'm going to do is I'm going to plug 13 in for the next step. So 13 times 2 is 26, plus 5 is 31. Then I'm going to plug 31 into this. So 31 times 2 is going to be 62, plus 5 is going to be 67. And this would be a recursive sequence. Each step, we basically are taking whatever we had and plugging it back in to get the next number in it. It's growing based off of the step that came before. Let's do another example. b1 is equal to 3, and we have that bn plus 1 is equal to 5 times bn minus 12. So again, we're going to start with 3. And then when we go up by 1, we are going to plug in here, and we're going to get 3 times 5 is going to be 15, minus 12 is going to give us 3. Okay? So then I'm going to plug that 3 back in. 3 times 5 is 15, minus 12 is going to give me 3. And then it's going to keep doing that. So in fact, this recursive sequence actually is giving me the each same number because once I plugged in 3, I was actually getting the same number out. So it basically got stuck at that step where it would continue to be 3 no matter how many times I go through the sequence. And that's it really for our review for calculus. So starting in the next lesson, we're going to be diving into actually doing some calculus, starting with limits. And this is why we need to know stuff like this with sequences, how to use natural logs, exponents, things like that, because we are going to be using it all in this course. And as I talked about previously, that is really where students mostly struggle with this course. It's not that they can't get down how to take a derivative. Most students pick that up fairly quickly. The problem is once you then have done this derivative, how do you then put it into a form that's useful? Or more specifically, if you have a really complex equation, can you simplify it to a form that you can use your rules for derivatives to solve for? Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.